so it's okay, yeah. My name is Alex Blanda. I work as a software security engineer for Intel's Open Source Technology Center here in Bucharest, Romania. The main topic for today is going to be Android fuzzing. What are the challenges, but also what are the opportunities in employing this type of process in this environment. These will be the main topics of the talk. So first, I'll try to give you a brief introduction into this concept. So we will discuss what is fuzzing. Then we'll see how to use this process in an Android environment. And what are some of the technical challenges? So we're going to go into a little bit into the technical field and see how to actually perform a fuzzing campaign in an Android environment. So let's begin. What is fuzzing? Generally speaking, fuzzing is considered to be a black box testing process. This means that we have little or no knowledge about the internals or the implementation of the system that we are targeting. However, in most cases, this is not entirely true. So in most cases, we can put fuzzing towards a gray box testing area because we have some information, we have some documentation or even access to the source code. The more information we have about the target, the better, because we can build better test cases that can yield better results. A general definition of fuzzing would be the process of sending corrupt or random data to a system and then checking how that system reacts to the input that we have provided it. The main purpose would be to find security-related problems. We are mainly looking for crashes. These would be the things that are of the most value to us, but there are also other things that may indicate strange behavior or abnormal behavior of the system. There are many ways in which we can use a fuzzing process. For example, depending on the type of input that an application accepts, we can have, for example, file format fuzzing for applications that consume input different types of file formats. The examples on the screen are exactly for this type of fuzzing, so we can test media players, document viewers, web browsers, stuff like this. We can also use fuzzing for other purposes. For example, if we have programs that take as input some data from the command line, we can use that as well. So we fuzz the data that program receives from the command line. This would be most useful in Linux environments, but it can also be used in Windows as well. So we have a command line in Windows as well. Depending on how much we know about the target system, we can have either dumb fuzzing or intelligent fuzzing. You would be surprised of the good results that a totally random fuzzer, so a fuzzer that has no idea about the internals of the system, the results that it can give. However, in most cases, we need to try to have as much info about the system that we are targeting as possible, because we are trying to basically to trick the system into believing that the input that we are feeding it is actually valid when it is actually not. So we've talked about different types of fuzzers. These are the things that we actually can expect to turn up during a fuzzing campaign. As I said, mainly we are looking for crashes, different types of memory corruption issues that can lead to segmentation fault signals, different types of arithmetic errors in the source code that could lead to different types of signals. Other problems could be denial of service situations. From a security perspective, a denial of service situation is not really a high priority issue, but think about the systems where it is critical that a certain component to run all the time. For example, industrial systems like SCADA systems or safety control systems, stuff like that. In those cases, denial of service situations can turn out to be a really big issue. Other things that we can look for are process hangs that can have behind them different types of synchronization issues or logic errors that can lead to infinite loops and stuff like that. Generally, each application has its own specific scenario. So each fuzzing campaign needs to be dealt with separately. However, there are certain guidelines or certain general steps that can be taken in any fuzzing scenario. These would be the general fuzzing steps that we would take in any type of fuzzing campaign. First, we need to do a sort of reconnaissance phase, like some research on the target. We need to identify the type of input that target can receive and what is the entry point in the system. By this I mean how can we actually send that input to the target. After we pass this initial phase, we can go and try to generate our malformed data or our random input in an automated manner. The execution phase is the actual fuzzing process. When we start and send, also in an automated manner, we start to send our data to the system. We need to have a system in place that actually monitors what happens with that system during the actual fuzzing process. So we need to have a way to determine how the system reacts and if there is something going wrong with the system. In a fortunate case, and for example in Android, in most of the time this is the case, we have a lot of crashes, let's say, a lot of issues. After a fuzzing campaign, let's say you start the fuzzing campaign today, you come back tomorrow, and you get thousands and thousands of crashes. You need to have an automated way to pass through all these results and sort out the unique issues. And not only sort out the unique issues, but also try to determine the severity of the unique issues that you have discovered. So from a security perspective, some of the issues may have a higher priority. So there may be issues that can lead to remote code execution or stuff like that. And there are other issues that may not lead to this type of situation. These first 6 steps would mainly be the fuzzing process per se. The next 2 steps would be what you do after you have sorted out all the issues. You try to debug them, see what actually went wrong, and then try to create a proof of concept, a working exploit for those issues, if it's the case or not. Let's go a little bit into Android fuzzing. So we can have 2 perspectives here. The first perspective would be fuzzing at the operating system level. So this is mainly intended for people that have contact directly with the vendors. So the people who need to ensure that the actual platform is secure. These are people like Samsung, Google, Intel, who need to make sure that the product, which is the actual Android OS, is a secure product. So we can perform fuzzing campaigns at different levels at this stage. We can perform at the kernel level, then higher up at the drivers, the system libraries, the Android runtime, and of course the application framework that allows the applications in Android to work as they intend to. Then we have the second perspective, the application level. This is a totally different story because it is a much more diverse environment. So we have a lot of people and a lot of companies that develop applications. We can really make sure that the applications that they develop are actually secure. So some may take into considerations different security aspects, some may not. Of course, there is the certain guidelines for the Android API that they can use, but we can never be sure. It's actually interesting because the applications can be considered as an entry point towards hacking the actual system. We, for example, had a project back at Intel where we would take huge amounts of applications and APKs, unzip them, so decompile them. We would take the compiled Java code, the .dex file, we tried to malform it based on the format of that file, and make it look as valid as possible to the target system, and then try to install it on the system to check how the Android install process really handles that type of input. Because the Android install process is actually one that runs with high system privileges, it was actually a very good idea to do this, because if we actually got some security flaws, it may lead to remote code execution as a privileged user. We actually got some pretty good issues, and we reported them back to Google, and they should be fixed in the latest Android versions. I'm going to give you an example of bug that can be found using this type of testing, so fuzzing. I'm not sure if you've heard about it, the stage fright bug. It was publicly disclosed last summer during Black Hat in the US by a private security company. The main idea for this bug was, and the scary part about this bug was, that it didn't require any type of user interaction. All the information that the attacker needed to know about you was your phone number. He could then send you an MMS message, and the way the Android OS is built, the MMS message would be parsed, and then the exploit could actually be run. Of course, there could be also other attack vectors. So, for example, you could browse from your mobile a malformed web page that would have embedded a video or an audio file that would start up that certain vulnerability. Although these things are generally bad, so if you have a very nasty vulnerability in your OS, that's not a good thing. If you have public exposure about these types of bugs, it can actually help the ecosystem. For example, after the public exposure of this bug, many vendors started to try and push updates faster towards their clients. So there is this problem in Android with fragmentation, where most of the people have Android versions that are 2 or 3 years old, and they don't really get to have any more security updates pushed to their phones. So this bug came a little bit as a shock to all of the people that were involved in Android development. For us at Intel, it wasn't really a surprise. So we were reporting issues in this library since sometimes in 2014. So we had an idea that this framework was actually pretty full of vulnerabilities. But in a way, the public exposure was a good thing for the Android ecosystem. Let's see some technical aspects about fuzzing in Android. So generally, there are the same steps. We have the data generation, the logging process, the triage, and then seeing what to do with the actual crashes. The data generation as well can be mutational or generational, which means that we can take an input that is already formed and try to malform it, or we can try to create it from scratch based on a certain format or a certain specification. Evolutionary fuzzing is a bit different. It tries to take into account, when building a test case, the response of the system. For example, it tries to take into account the code coverage that it achieves during testing. So for example, if a test case reached a certain branch of the code, the next one tries to reach further. This would be only an example. There are many tools, open source tools that can be used. The ones on the screen are just some examples. The most popular of all is really the American Fuzzy Lab. It is very, very powerful, and it is in a way an evolutionary fuzzing tool. So it tries to achieve as much code coverage as it can. The logging process in Android, as you know, or as you may not know, if you're familiar with Android, there is the buffer, the lockat buffer, that collects all the information about system processes and application processes with different priorities, like fatal, debug, error, and stuff like that. There are in total 7 priorities. What we can do in any fuzzing campaign in an Android environment is, before actually sending a test case, either if it's fuzzing an application or fuzzing a system component, before actually sending a test case to the target component to be executed, we artificially insert a message with a fatal priority in the lockat buffer. So when we actually encounter a fatal message that was generated by the system, we will know that it will be caused by exactly the test case that was above. For example, in the case of stage fright fuzzing or media fuzzing, when we try to send a media file, a malformed media file, to be decoded by the specific decoding library is in Android, we send a message containing exactly the name of the media file that we have tried to execute on the device. That would be the main idea for the logging process. For the triage mechanism, so we said we are looking for crashes. Each time a crash occurs in Android, an entry is generated in data tombstones, which actually contains valid information about that specific crash. It contains a lot of information, the type of signal that was generated, the backtrace, the state of the registries, and stuff like that, the process that actually died. What is of interest to us is the program counter of the last entry in the backtrace. We can take that value and actually uniquely identify a crash by that value. So if we have an automated process that takes, let's say, 1 day, and we log everything we've done using the logging mechanism that I've talked about earlier, we can then employ another automated process, a triage mechanism, that would go and take all the crashing test cases, parse the associated tombstone, and grab the program counter value and check if it has been previously encountered or not. This is a simple way to actually see if that crashing test case occurred before or not. After triaging, we need to actually analyze and debug the issues. First, we have the data tombstone file that I've talked about earlier. We can get some information from here. Other things that we can do, we can check out the message. We can see what type of error was generated and see if it was a write error or it was a read error. Essentially, what happened. This would give us a first hint if that issue is exploitable or not. We can debug the issues using GDB. We can attach it to a running process or actually start the process inside a GDB server and then attach it from the local machine using normal GDB. The process, besides using GDB server and GDB like in a remote connection, is basically the same with debugging any issue in a Linux environment using GDB. We have address to line. Because Android is in a way an open source project, we have basically access to the source code. So we can actually map the specific crash to an actual line of code in the Android open source project tree. Using address to line, we can take the program counter value from the tombstone and this will allow us to map it to a source code line. If you are interested in this type of project, we have released some open source tools at Intel. These are basically tools for fuzzing specifically in Android. You have a stage-right framework fuzzer, broadcast intent fuzzer, and a module for another very popular open source tool, which is Drowser. You can check it out at github.com/fuzzing. Feel free if you see something you like. And these are my contact details. If you have any questions, we have some prizes from our friends at OWASP, some balls and stuff like that.
Thank you very much, Alexandru, first of all. Are we going to launch those?
I don't know. We can try.
Does he have a launcher? I can use your fingers, I guess.
Yeah.
Okay, questions?
Hi, I have a question.
Yeah.
You mentioned earlier that you can have address to line tool. My question is, Android doesn't use ASLR, so the addresses are not randomized. How does this work?
Actually, Android uses ASLR. It's a very good question. Before, I didn't delve into the details, but before actually starting a fuzzing campaign, to make sure that the PC address is actually unique for each crash, we turn off the ASLR for Android. Yeah, sure. Yeah, I'm gonna give him. Yeah. Sorry.
Any other question? No? Shall we throw these in?
Yeah. We can throw them.
So you need to ask a question now. Sorry. No? Okay, cool.
Okay. Thank you very much.
Thank you very much, Alex.
Thanks.